We are going to get started right now, and we will be answering questions at the end of the session. If you write them down, that would be great. I can ask them to Gilles at the end. So we're talking about boosting efficiency with Creo automation, specifically for sheet metal. And we have here today is Gilles will be presenting. Gilles is our director of the technical director in Europe. He's been with SIGMAXIM for quite a while. And before that, he was at PTC as a sheet metal product owner. And so his experience with sheet metal is very vast. All right, and a little bit about our company, about SIGMAXIM. We've been in business since 2001. We're headquartered in Boston, but we are a global organization with locations in Europe and Asia. PTC service and software partner. And at this time, our customers probably have a million plus applications running on our platform. Our corporate mission is to really eliminate non-value added work inside of Creo. So it's about automating things, one block at a time. So you can take a task and then have a bunch of tasks automated and then have those tasks call other tasks so that you can have a very sophisticated automation in a very straightforward manner. We call this our building block approach to automation. So basically, people come to us and say, can I automate this in Creo? And anything that you can do in Creo can be automated. Now, we kind of break those into different methodologies. A lot of people come for us for on-demand product build, but that also extends to engineer to order. And some people are looking to replace virtual master models based on some of the limitations that they have. We can virtualize it and remove those barriers. MBD, we have automation and tools to support your journey there. I kind of call the sheet metal one kind of best practices and standards, getting your specific rules into Creo so they happen correctly each and every time. And that kind of leads down into our manufacturing automation as well, as we take those processes, documentation, and procedures and automate them.
Yep. So thank you, Jennifer.
So now I'll turn it over to Gilles to get started.
Thank you. So today we'll be presenting something that is a kind of a different approach in automation, which is not automating of a product, of a full product that is well known in advance. It's about automation of process bricks, process blocks to go to make different models. So it's really like a process automation. I will talk about the toolbox, and because that's a toolbox, that's a collection of tools to help people to work with sheet metal constraints, capabilities, etc. So basically, there are 6 main items that we will cover today, maybe a little more actually, but that's the 6 main areas that we will talk about, which are number 1, reusing standards. So what are standards? Standards could be standard models, standard templates. So when generating sheet metal model, it's very often to generate covers, to generate doors, to generate, those kind of things. So why restarting a new model when you can leverage something that is existing? Then it's about features, features about how we could add safety to the models, because it's a big deal, safety, because if your customer or if your worker is getting hurt, then the company will have trouble. So that's really something that to look at about. We're looking about some cost-saving manufacturability features, so making models more rigid, more easy to make, making sure that everything is well prepared so that the cost will be reduced at the end of the day. Then we will talk about reusing components, reusing standards, or using standards. What kind of standards, like pen insert, like placing specific item that you place all over the time on your designs, and getting along with all the constraints that you may have. We will illustrate an example working across different organizations in the company, where we will describe an electric design office and a mechanical design office, how those two could communicate to generate some information. And then depending on if you are in a make or in a buy situation, there might be different processes, there might be different stuff that you need to comply with to make sure that your models are feasible, your model are at a better cost, etc. So basically, our toolbox could be presented something like that. So this is the main item that we will cover today. We'll start with standard shape reutilization. Then we'll work about those features, different kind of features, specific feature for safety, specific feature for constraining models to assemble them together, specific features to generate specific holding items, specific rigidity item, etc. Then we'll move to the PEM insert and etc. So I'm presenting those 1, 2, 3, 4 items first, because I will run a video for that is covering all those 4 items together, and I will talk about. So basically here, starting new models. When you start a new design, when you want to add a component to your design, there might be, in the sheet metal world at least, a possibility that what you're trying to do is something you've done already in the past. So if this is something you've done in the past, then why not simply reusing it, automating it, being able to simply select items in an assembly or outside of an assembly to generate it, so that the model tree is the same, the parameters are valid, everything is compliant with your methodologies. And here, this is what we're illustrating with this box. This box could be 1, 2, 3 bands. It's placed now in the assembly. We go to the easiest of them, the flat one, just a flat sheet of metal that could be placed quite easily in the assembly as well. The main thing here is trying to go fast to the point, generate whatever you need to generate, place it in the assembly that needs to be targeted as an assembly, and place the item. So you see still those items are very simple. They are basic elements. We could make compositions of those basic elements, like the box, like the flat, like etc. We illustrate this with the door that we're about to design here. What is a door? A door is a box that is held by hinges, and that includes a key lock. So we're the system then you're reusing in the background the automation for the box, placing the box, 1, 2, 3 bands, depending on what the setup was done, placing the items that are necessary to define what so-called door. So the items are generated with the hinges, and placing some of those items there. And you see that every time that we will be adding standard elements, standard components like hinges, like key locks, like all those kind of things, the necessary cutout will be generated. And automation for starting models is as well very convenient for those models that you are not doing enough, that you're doing once in a while, but that are a little bit complicated for you to redo every time. And here it's an example of this item here is in blended part, which goes from rectangle to round. Then it goes to this rectangle to round, generate a full 2D drawing, detailed, with one folio with the full information in 3D and a small flat pattern. And then the flat pattern, scale 1, just to export it on the DXF or IGES or whatsoever with the next player in the process. Now we're good. We have created our models. We can continue now to add some features. The first features I'd like to introduce is some safety features. The very point to get in memory here is that all of those buttons that you see on screen, all of those automation that you see on screen are tailored, are made to your requirement, Mr. Customer. So you decide what you need. It's not just like a plugin solution that you just take and plug in and play it. It's something that you could add, you can extend, you can add as many information as you want. And that's why I'm saying we're showing some safety features like those flushed hand that we did on the right one that we will repeat in here. This thing was made with one technique, which is not asking any dimension to the customer, to the final user, I mean, because we want to force him to use like standard values, standard dimensions. But of course, you have the full control working with us, teaching to you how to make those things as well. We could explain you how to make those things variable so that you can make the changes to them. So here, example, we place two flushes. That really are safety features, basically. And here we're adding some rounds to break the corners, break those edges. Funny enough, PTC had made this automatic round on solid models, but did nothing for sheet metal in this area, where this is very specific and where this is very useful. A lot of companies are breaking the edge like that, adding some corners, some rounds like that. And as every tool that you will see here, it's always possible to have them work on a model, to work on a list of models. So here I'm selecting two of them, and the system will apply the automation to both of those models to generate for us the required rounds where we need them. The bottom line here is that the main keyword is that this thing is standard to your company. You're using a tool that is a quarter of an inch. You're using a tool that is a radius of 2 millimeters. You're using a tool that is a whatever other unit. You define your own setups, and then your user will use it because it's easier for them to use it. And you will use always the same values. So it provides consistency from the design to the manufacturing. The next set of features I'd like to mention is some examples of showing how to locate the models. How to locate the model first, why not putting screws and holding the models with those? So for instance here, along the edge of the model, we want to distribute 3 screws with the dimension scheme that was drawn on the image on the GUI. And this is what is happening here. Adding the items, we will add 2 more times this here, adding 4 in the other direction and 4 on the left side. Okay. And then what is the result? The result is simply adding the necessary hardware that you need, so those screws, adding the necessary cutouts that you need to have the screws go through the models, making sure that the holes are looking to each other. There is no separation. There is no error. Holes are in front of holes. Screws are in front of holes, so the thing can be mounted. Another typical way of placing components before welding, for example, is just to add like tenon and mortise, like add some tabs that goes into holes, rectangular holes. That is made just to hold the part in position, maybe just to hold it before you weld, or maybe just to hold it forever, whatever. So that's an example here showing this kind of capabilities with chosen dimensions, where this model has tabs added, and where the related model, the related models on the other side were cut out with rectangle items. So you see all the details here. So the main point here is holding the models. Any kind of techniques, any kind of trick that you're using in-house could be replicated and automated, so that we will be using the same kind of placement. It's saving time and quality to your users to place those items. So you already realize here that we have no automatic model creation here. It's just about generating features. What is repeatable in this process, in this toolbox, is the features that you're using. So the automation here is adding some missing information on a dedicated sheet metal package, and we're adding those things. And now we continue, so on and so forth, with new kind of features like what I'm naming cost saving of rigidity. When a flat sheet of metal like this is too floppy, then you have the choice on either making it thicker, and that it has a cost, or adding some machining, some manufacturing on it, maybe here to add some rigidity on it, so that it will be making the job the same way with the same amount of material. Okay, so all those items, you should view all those items in the lists that are presented as your most used capabilities, your most used features. And those most used features will be repeated the same way for every users. there will be no differences. There will be no searching. From a new user taking back the job, it will find out the same kind of model tree, the same quality on the models, etc. So this kind of shape is as well quite used in the industry to put some rigidity in the bend. And here it's an example showing how easy it is to add, change, remove, etc. We put in on the top, and let's add one in the bottom. Okay, again, view this as some examples. This list of tools, this library can be extended as much as you want, as much as is possible. And about those features, we will finish those kind of features with what I named the deformation control. So we know that in every band, in every side of the band, there will be a little deformation of the material. This little deformation might be okay. So in those areas here, specifically where we're clicking here, in those round areas. And those little deformation might be fully acceptable. Most of the time it is fully acceptable. Sometimes it's not acceptable for some specific design reasons. And because it's not acceptable here, we have decided to add those kind of new features to control the deformation. Those are as well very specific sheet metal items, sheet metal features that are added to make sure that everything will be welded correctly, everything will be fitting together correctly, etc. Another one that is very usual as well is when you have a cut that is too close to a band. For example, just generating this hole now for the example. Then you might decide to put some band relief cutout. So it means that the deformation that could have happened without this cut, deformation on the hole here, then will be avoided thanks to this feature that we have here. I look like my keyboard will give up. Okay, let's branch. Okay, so again, I'm presenting those features one by one, but really what is the message behind is that whatever those features are, they are what you need. You are, as a customer, as a user, you are driving what are the most used, what are the most useful items that you need. And we will enhance, we will continue to put those libraries up with more and more and more tools so that it's helping everyday's life for the sheet metal designers. Now we start to address the standard components that are used every day on the sheet metal models. The number one in the list is the PEM inserts, the PEM inserts actually. So based on the library that is defined with an Excel file, with a database, whatever, we have the possibility to just search the model. But before we do that, I'm just showing this. We have moved the box that was the box as a part. We moved it as a box as a sub-assembly, just to support the process of the PEM insert, just to make sure, it's not this one, that's this one, yeah. Just to support the process of being able to generate a 2D drawing to represent the information for the shop floor. And here we go. The system is proposing a list from a database of what is compatible with the material, compatible with the thickness of this metal, to present something that is not randomly chosen. Again, it's selected from a database of a complete list of PEM insert with what is compatible with this thickness, what is compatible with this material. We're placing a few of them here. This database, this list, could be extended and tremendously. I mean, you can add anything. And if we look, in the video, we didn't look into the models, but for instance, if we look to those models, you would realize that they are step import models. They are not Creo models, which makes no difference really, because what is really important is how to place, where to place, and what to cut out to place them in an efficient manner. So that's our PEM assembly. And we could have any model from your company as standard. So we could support any standard. We saw that a little bit on the door The hinges are some standard. The key lock is a standard. And why not this fan, this ventilator here? So this ventilator, want to place it, you are doing covers for electrical equipment. You need to cool them down a little bit. You're probably using ventilators. And if you're using ventilators, you probably need to generate those kind of specific features, specific places to let the air flow in. So again, this is something that is fully controlled, where whatever the standard that you're using are, if they have some impact on the sheet metal, on the part, on the models. And by the way, I'm mentioning sheet metal today because we are only focusing on sheet metal, but everything I'm saying is as well applying to any kind of solid model, any kind of assemblies, any kind of sub-assemblies, etc. So as soon as you have a standard, the standard could be attached with information about where to place, how to place, what to cut, what to add. Maybe you should add screws, bolts, nuts, whatsoever, and that's the possibility that we have. Here, placing a second one. Again, that's another kind of standard that might be used often. And if it's a standard that is used often, then it's worth it to make it like that. Okay. Looking at the model, the door, and if we look again at the part, the part is up to date and everything is in space. Good. As we have standard component, we may use standard shapes. It's especially true for people using punching machines. If you're punching, you don't want the user to use any kind of dimensions. You probably want to convince the user to use already defined tools, already defined dimensions that are compliant with your manufacturing capabilities. So we are illustrating this in here with selecting standard shapes. This time it's just regular punches, so you're not generating that much of a geometry. It's just a cutout. It's a simple cutout. But the thing that is here is that it's something that has been validated, that is standard, that is something that has been for sure present in the shop floor, something that you can use in the shop floor. You have the tool basically. So of course the user can deviate, and we will see this later how we could manage that. But at least here he has some capabilities, some opportunities to select something that is from the standard. Okay. So we're placing this clip, placing a second one close to it, just for the fun of it. It's another clip. Again, everything that is coming from this list, from those lists that you see here, are information stored in database. So it means this list of shapes, this list of dimensions is fully driven by the company itself. It's not driven by us, it's driven by your company. For instance, and just to conclude, some people are doing ventings with those grid tools. And this grid tool here, for instance, is generating in one punch several drillings. This is a special tool. Doing that, poof, here we go. It's generating a grid in one shot. Okay. Good. So we have covered up to now the standard shape, the specific features. So we've seen many of them, plenty of them. We have covered the libraries of features. Again, we have covered standard component and standard features as well. I'd like to illustrate now an example of collaboration between this electrical office and this mechanical design office. This is a project we had to run through in the past, where some kind of configurator was given to the electric people, and the electrician guys were defining basically the dimensions of this very common object that they designed, the electric box. So they just have a very easy to use Excel example here, where they're placing the different components that they need, or placing an interrupter, placing a green light, etc., placing all those items all together. That's the job from the electric people. Then they send this Excel spreadsheet to the mechanical engineer, and the mechanical engineer will just read it. And what I name a baby configurator, so a small configurator will run, interpreting everything that is into this Excel file to generate everything that we need. It means generating the assembly, placing the component, generating the necessary 2D drawings, and optionally, and it was done in this example, placing the item into the assembly with the possibility, of course, to set it up in the right position and to fix it on the right position with sheet metal in-house capabilities. So the part was generated, it was put in place, and if we look in the back, I will probably hit stop here, up. You see on the top there are 2 hooks, in the bottom there are 2 PEM inserts that are really added to the back plate so that it can hold the complete assembly. Okay. Here, that's an important thing. You might not be alone in the company. You might not be the only design center. There might be other people. And what I want to insist on this in this stage here is that the solution that we have is completely open. It's completely open to read in, to push out information in and out from other departments. It could be in the form of an Excel file. It could be something more elaborate using your ERP system. It could be something using web services, files, JSON, XML, whatever you name it, we can support, we can read. Okay. I will skip this preparing and we'll skip it and keep it for last presentation, this one, because it's related to a customer case. So I will talk about the customer case after presenting this as an introduction. And just would like to push on other capabilities about manufacturing. So the last band here with the 3 items is really about manufacturing. Manufacturing about checking if the part can be bent, unbent, and eventually generating the bending process. Being able to check the validity of the model, fix the validity of the model, and then why not go to the complete CNC manufacturing. So let's start with the bending process. So as we have the full control with our solution with Creo parametric, we're able then to define any kind of extra application that you might need for your day-to-day work. For instance, here, we had this request in the past to generate a bending tool, something that will make the programming or that will help to prepare the programming of the press brake. And what is important in the press brake is what kind of tool, okay, what kind of dimension to set up from the bend to the stop of the press brake, and check if there is any collision with the tool and the part. And we will continue like this. So I will skip a little bit because it's a little long, and this is continuing on every side. Bloom, 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 bloom. And then here we could just run the movie. So it's a kind of the summary of everything that was done. Placing the tool, getting the dimension, showing the dimension for the setup of the press brake, and making the simulation of the bending process to check that everything will work and there will be no collisions. Once this verification is done, it's then very easy to either export a specific DXF that includes the bending information or generate a 2D drawing with multiple view per sheet or just 1 sheet per view or per band. Here, for instance, we decided to get 1 sheet per band. And here we have the, the explanation, before on the left, after on the right, explaining where is the stopping surface and what is the dimension to respect. And showing on the top right as well, the view of the part after the band is realized. Okay. So this is typically here, and we did something similar on the nautic industry for wood. The people we are really working with specific features, specific requirements, we are missing some information in Creo. Creo is great. It can do a lot of things. It's just not optimized for wood. It's just not optimized sometimes for sheet metal. So our role at SIGMAXIM is really to help to build up those informations and to add those things so that you become more efficient in your company. Okay. Checking the validity of the model is interesting. Now, there are plenty of rules on the sheet metal model. It's especially true for forms. A form should not be too close to another one. It should not, forms and punches should not be too close from a border. It should not be too close from a band. So it's especially what I said true for forms, because when you hit the first form, it works. When on the punching machine, you will hit the second form. If it's too close to the other one, the tool might flush down the first punched area element. So this is really something that needs to be checked. It's really a feasibility thing. And if a cut or if a form of something is too close to a band, we know for sure that there will be some deformation, and the part in reality will not look like the part in the 3D design. Okay, Cancer. So here I was putting together another movie to show the different kind of checkings that are really useful and commonly used in the punching industry, for example. Number one, when you're about to release a model, your company has some tools. Those tools might be in the shop floor or they might not be in the shop floor. So here you see the list makes no doubt for a user that some shapes are recognized, and some shapes are recognized, but they are recognized as non-standard, which means the big rectangle that is here near my mouse is probably not feasible with one single hit, with one single tool. So either the designer will decide that this is what he needs and he will not change it, or the designer will say, oh, by the way, I can change this a little bit, then it will fit with the standard tool that we have in-house. So that's really the first level of verification, making sure it's feasible in-house, for example. The second information here is to clean the geometry from Creo Parametric. You see here, there is some funky shape here and here. If you're using punching, even laser, those funky shape will be realized, and you probably don't want that. So you probably want to have something that is more natural, more smooth. So basically here as well, we have the possibility to explore the full geometry of the models, whatever they are, sheet metal, plastic, solids, whatever. So when we are doing this analysis, we can locate those problematic areas and propose some solutions. And you see here, now the funky shapes has been removed and the thing was been replaced with something that is straight and smooth. So here it's a single punching line, here it's a single punching line, here it's a single punching line, etc. This is what I mean by cleaning up the geometry, the Creo parametric geometry. And checking before punching, it's something somehow like a double as what we just showed before, that we were showing before. When you have like items on a sheet metal plate, well, you want to know if it's feasible, if when you will hit this item, it will not hurt this one, and when you hit this one, it will not hurt that one, etc., etc., or the other way around. So there are multiple solutions. The one solution was here to attach the information about the tool size around the elements, and we visually here can see with no doubt that there will be some collision and that we will have some problems. But as well, we could use the tool that we were using before. We could use this tool here that has been generated on some other occasion. That is as well showing some kind of highlighting, explaining these are too close to each other, this is too close to the side, the other two one are too close to each other, etc., etc. Okay. And with the possibility, of course, over time to generate some more kind of reporting so that everything is fine and clear. The last thing I'd like to mention in this video, before we go to CNC manufacturing, this is about what about a model that is created in Creo parametric and that will be machined by a different solution. It will be machined by something that is not Creo NC sheet metal. So we probably need to prepare this model a specific way to help either the user using this non-Creo NC sheet metal application or this extra piece of software to help it to recognize the tools that we have. If we just speak about the hooks, if you go with Creo, you just flatten them and that's it, and you export the DXF and you think it's good. But in reality, the other solution that receives the DXF file, you may help it by just sending it like symbolic representations, symbolic shapes. For example, here, the form was not able to travel through the DXF, but this symbolic shape is just a regular 2D contour that will be able to travel through the DXF. And on the other side, the CNC piece of software that is receiving this information will be able to recognize and apply the proper tool. This symbolic shape is actually in replacement of this hook. So the other piece of software that is unrelated, that is not connected to Creo parametric, will recognize that and will be able to place the proper tool in the proper location. Okay. And if now you are lucky enough to get CNC Creo NC sheet metal, it is as well a possibility to automate the complete process from the design to the manufacturing. Here, what is happening, the solution is searching all sheet metal models from the assembly. It's organizing them by thickness, and then it's preparing a nesting. And the nesting then will be used to automatically generate a laser toolpath on it. Here we did a laser toolpath. And we have the simulation of this laser machining that is done here. Okay. So in short, if we go to this manufacturing, you see that we can handle everything from the design to the manufacturing through the 2D drawings, and we will spend a little more time now on the 2D drawings, through automation. So everything you can do manually in Creo parametric, we can reproduce and we can help you to do it automatic. Okay. So I'm jumping back on this 2D drawing here. So I was keeping this one for the end because it's related to a case study that I will present. So we had this company customer, Atlantic Group. We were asking us to help them to generate 2D drawings. In their opinion, the models are always different, but the way to generate the 2D drawings is always the same for them. So we worked on a solution to first prepare the model, and this is what we are doing here. We are preparing the model. What does it mean, preparing the model? Preparing the model means having specific orientations created. It means having a flat pattern generated in a specific way. That's it. So if we open one of the model here, you'll see that we have like specific orientations existing. The ISO view, the isometric view is really created in a specific way with specific angles for them. And we have this simplified rep with the flat pattern. Okay. Once this is done, when every model is prepared, then the user, final user, can launch the complete 2D drawing generation. So GUI is presenting to him the models organized by something. Here they are organized by some status parameter. So the status gives them some information about do we need it, don't we need it, is it something that is modified, etc. So that's really what it is about. Okay, and then from that list, it will simply select and ask the generation of all the 2D drawings. And now it starts. The user can go get a coffee because each and every model of the assembly is used to generate a 2D drawing. So in this video, we have retained a few of them, maybe a dozen of them. And you see it's quite fast. It's generating all those items with always the same principle. 2 pages 2D drawing. Page 1, a detailed drawing with 3D views and a small flat view. And page 2, a scale 1, no border 3D view. So this is page 1. Dimensions are added automatically, and page 2, the 2D flat pattern with no border for the EDXF output. All dimensions, outline dimensions, band dimensions have been added, and the requirement from this customer was to add band dimensions that can be measured with the caliper. So all the dimensions that have been placed here are dimensions that can be measured with the caliper. And so with this customer, so we want to introduce the Atlantic Group, basically, who they are. They are a very young company because I'm the same age, so it's very young. They are global. They're working with multiple brands. And what are they doing? They are doing all of that. They are doing a lot of different things with something that is very common, a lot of sheet metal models, a lot of sheet metal parts. So they were asking us to generate those automations because in their vision, they were starting to do some automation themselves using map keys. And of course, map keys has some limitations, and they were reaching the very far end of what they could have done with map keys. So still, they were going fast, but they were not going fast enough. They were going quality, but they were not going to quality enough. So they were looking for something else. So we went and worked with them, and this is those images are some kind of a recap of the videos that we saw, the video that we saw just before. They made some measurement, and they gave us this table for information. So they compare before, here it's before with the map keys automation. After, it's with the automation that we've done with them. They measured 4 times faster, again 4 times, which means that preparing a module, preparing a part goes from 4 minutes to 1 minute, which is not very big. 4 minutes, 3 minutes, this is not a very huge gain, but every product that they release, and they release a lot of products per year. Every product is about 10 to 15 days, 2 to 3 weeks of work to just complete the 2D drawings. So for this product, 𝗬𝗠𝗬𝗧 here, they made a measurement. They moved from 12 days to 3 days. So here it starts to be very interesting for them, because then they can use this time for something else. And then they had like other benefits. And the other benefits is that, number 1 was the 2D drawings that were generated were all looking the same. They were all using the same template, the same format. So when the 2D drawings lands in the shop floor, the guys in the shop floor have a better understanding because it's all the same way. It's all the same logic that is used behind the scene. So they don't have to do any exercise of interpretation. Another thing that they wanted to do, so that's basically those 2 points. Another thing that they wanted to do is really, they wanted to go away from the table drawings. When you have a family table, you do 1 drawing, 1 sheet, plus a table that is listing all the different items, all the different values. And they were qualifying this as error prone for them. It was really generating some misunderstandings, sometimes some errors in the shop floor because people are not looking in the right line, etc. So they wanted to go out of that. Did they do it? No, they were not doing it because it was too long. They didn't want to enter this thing. But now they could have done this because it's fully automated, so it's gone. And they moved from a 30 manual actions with all the map keys that are error prone, that are no value added, that are very boring, to a known, which is the full automation. With the conclusion for them, just like this, is that, okay, what was the need for them? So the needs were what I said, but it's recapped in here. Reduce the time for the preparation, remove the non-value added. We want the people to have more time to do something else. We want to have people to have more time to dedicate themselves in improving designs and not just spending time on making 2D drawings. No more table drawing, which was a big win for them, a huge win for them, and something standardized that looks always the same. So we did this application for them. And the result in here, we are not, SIGMAXIM is not writing, the company is writing. So they reduced the activity of making drawings by 4, which means that an activity that was occupying the design office 20% of the time in the past was reduced to 5% of the time. And those 15% of the time now are dedicated to make design, to improve the solutions, to make more product. The company has been challenged to increase the number of products in the coming 5 years. I think they have a 5-year plan to double or triple. I don't know exactly what is the exact number, the number of products they have to release. And if they have to go in that way and to double or triple the number of products they release, then they will have to save some time a little bit here and there, or hire 2 or 3 times the number of engineers, which might or might not work, right? Okay. So as a conclusion of this presentation, before we move to the Q&A, is like, we have presented you today something that is only dedicated to sheet metal. SIGMAXIM is able to work on all areas that PTC Creo Parametric can touch. Jennifer was introducing you this at the beginning, talking about MBD, talking about virtual master model, talking about generating virtual twins, I mean, we can cover everything. Today, we just were covering sheet metal as an example of where we can help you.
Thank you so much, Gilles. If anybody wants to raise a hand, if they have a question, if not, I will take some of the written down questions. So basically, is this easy to change the tools so that the standardization meets our company standardization? And will it cause too much restriction and prevent innovation?
Okay. So, as you've seen, the tools are like a collection of tools. This is a toolbox. We have a solution that is fully open. It means that it is readable. You can change it. You can read it. We can teach you how to use it. So with that respect, number one, it's not closed. You're able to do whatever you want with this solution once you're trained. Is it easy to add a new tool? Yes, it's easy to add a new tool. The tool might be a little bit more complex, but it's easy to add a new tool. So some tools are very easy, create specific shapes based on databases. Some tools might be a little bit more complex, like generating full geometry analysis, checking this or that. I don't know what exactly, but checking things that are different, that are based on the geometry. This is where we could have a mix of you can do it, we can teach you how to do it, and we can do it for you because we have more experience on the tool. We are not smarter than you are. We are just doing this since like 20, 22, 24 years, and days and nights. So we are very used to those exercise of making those automation. So it's very easy to add a new tool. And the language we use to generate those tools is really, really close to the Creo language. We name it Creo English, by the way. So it's really close. So the scripting, the writing of those rules is really something close to Creo Parametric. Will it add restrictions? No, no. You've seen what we've done here is really proposing some solutions to a user to go faster generating this or that. But the final result is a Creo geometry. It is a Creo geometry. So the user may want to use this automation and modify it after, because he needs something very special, or he might just not use it and work manually as before, and the tools will continue to work later. So there is no restriction, and this is not slowing down the innovation from the company. It is giving more air, it is giving more time for innovation, because you are just removing those unnecessary time-consuming things.
All right, and how does this tool differ from like a model check, Gilles?
Okay, model check. So model check is a solution integrated with Creo Parametric that is basically able to check what? To check the feature names, if the feature is there or not there, is it in the right order, do I have the right layers? More or less, that's the kind of thing that model check is doing. Do I have the right parameter, etc. This is about the preparation of the data, but there is nothing about the geometry. So with our solution, we could work together with model check because we can communicate with model check and we can have this thing. So there is no point about fighting against each other, and we can complement it. So we can replace it. Why not? It's something that everything that they can do, we can. But if it's not something expected, we can just cope with it. No problem. We will just add what model check is not able to do. And what is model check not able to do? It's not able to work on the geometry, understand the geometry. You've seen those searching on the punching sizes. You've seen that the dimensions from a form to a band, a form to another form. This is typically the kind of thing that model check will not be able to do. So we will help adding those kind of information on top of the other tests that model check is doing.
All right, and one last question. We have a single laser machine and multiple machine punching. Can we easily switch a model from one manufacturing destination to another one?
Alors, yes, of course. So we had this company in Europe that was having like 3 different lines of production, and each production line had specific capabilities. Depending on which one was loaded, they could take the product that was planned to go on line number 1, but line number 1 is loaded, so we need to move it to line number 2. That's really what it was. So it's quite easy to check on the models, as you've seen, and to realize, number 1, is a model compatible for line number 1 or line number 2 or line number 3 or 2 or 3 of them at the same time. So that's number 1. Number 2, it's able to check and show what is compliant or not compliant. So let's say that you were preparing for laser and now you want to move for punching or reverse. Then what is not compliant, what will not work. And number 3, it could help you, it could propose you solutions to fix some items. I would give an example of this illustration like we showed just before, the funky shape I was talking about. If you're moving from a laser which has no problem in machining those funky shape to punching, then you've seen that we have a tool that is helping to make this conversion, to make this thing more punchable, punch friendly. Yeah.
Perfect. Any other questions? Anyone with questions in the audience? Perfect. Everyone, thank you so much. Feel free to reach out to me. My name is Jennifer Sanders, and I can be reached. You can connect with me through LinkedIn or give me a call at our office number. Check out our website. You can do a contact me. And I look forward to hopefully speaking to you guys in the future. All right. Thank you so much.
Thank you. Bye-bye.